Oh, hi there. Let's get started on describing and graphing combinations of transformations. So this is really taking all the skills we've learned about stretches and reflections and translations and putting it all together. So let's go. Let's take apart this example here where you've got g of x is equal to blah, 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 blah. All that stuff. So when we see something like this is the skill that we want to develop. We want to be able to look at this weird equation here. Notice, first of all, that g of x is a transformed quadratic function. I can see that it's got an x squared in there. It's a quadratic. Which quadratic? Well, we could expand and work our algebra to find the equation. We're going to do that too because I can't resist. But we also want to be able to look at it and say, you know what? I'm really good at creating tables of values and graphs of y equals x squared. Here's y equals x squared. And then I want to know, if I was working visually, how would I need to change that to make it this new function? So let's articulate all of our different transformations that we're doing here. And I'll use typing because it's better than reading my weird writing. All right. So the first transformations that you're ever going to apply when transforming functions start with the multiplicative ones, the ones that operate by multiplying inputs or outputs. Those are your A transformations and your K transformations. Visually, those are stretches and reflections. So I notice that g of x has minus 2 in front. That's an A transformation. So we could say first reflect in the x-axis or y-axis. I can't remember. This is the x-axis it's going to reflect in because it's an A transformation. It changes your y values. Reflect in the x-axis and stretch vertically by factor 2. Okay, and that's a result of A equals negative 2. That's the number that's doing this transformation, this negative 2 right here. And then what's next? What will we do next? Well, it doesn't matter which order you do your stretches and reflections, just that they happen before your translations. So now we're going to need to do the K transformation as well. And we could have done them second and first or first and second. It doesn't matter which one we do first because one's changing X values and the other one is changing Y values. So they'll change things that are independent of one another. Well, second. And this 3, I forget, that 3, when it's a K is 3, does that stretch it out along the x-axis or squeeze it towards the y-axis? The K values squeeze for some weird reason. So, well, there's not a weird reason, there's an algebraic reason. But if it feels weird, that's okay. Second, compress the function horizontally by factor. And if you said compress by factor 3, I think that's okay. If you said compress by factor 1/3, I think that's okay. People will like, if I say stretch, I would say stretch by factor 3, and compress by factor 1/3. I think that's fine. 1/3, and that's a result of K being 3. There we go. Now we've done all of our stretches and compressions. So let's take a look at what's happening to our function over there. If we were working visually, we would have the function first flipping in the x-axis and being stretched by factor 2. So that's something like this. That's stretched by factor 2. And then it's squeezed in towards the y-axis. So it's even narrower. It's like this now. Oh, that's such a big stretch factor. Wow, it's so stretched. All right. And then we're going to take the whole shape, so we might just grab the vertex and move it around and translate it. Where is this vertex going to translate to? Third, translate is the math word. Translate the whole function. You want to do the D first or the C first? It doesn't matter. You get these choices in your day. I'm just giving you a choice. That's actually a meaningless choice. It's like, do you want to put your right shoe on or your left shoe on first? Which one? You get to choose. You have so much freedom. No one's chosen yet. D, thank you. So we're going to move by this -2. This D value here is subtracting from our inputs. What's that going to do to the function? X minus 2. Moves it to the right. Yeah, and when we subtract, it moves to the right. Translate the whole function to the right. 2 units. That's a result of D being equal to 2. Notice I flip the sign as I pull D out. And then fourth, translate the whole function. This is the C value. It's -1. Is that one a sign flipper? No. Okay, good. You sounds like you guys know what's going on. Yeah. So translate the whole function downwards 1 unit. This is a result of C being equal to -1. So then we're going to have just this vertex point here, the final color. There it is. Boop. Purple. Okay. It moves to the right 2 and down 1. So it's like now over here. And it's super, super stretchy. So it's like this is our final function. I'm expecting something that has a really big negative a value, well, relatively big negative a value, and has a vertex at 2, -1. That's the kind of function that I would expect. And now let's calculate the new equation. Okay, let's figure it out. So the steps to do that is we're going to copy out this equation, g of x is equal to -2 multiplied by square bracket. Don't use square brackets in Desmos. X minus 2, but definitely use square brackets in your own work because it's very clear that that's the outermost bracket. So that's very good. So we're going to have that. We'll just copy out the function carefully. And then you are going to just simplify it down to, making sure that it's not in some weird form, but some form that we recognize. Vertex form, factored form, standard form, pretty much equally useful in different ways. So let's get it to vertex form. It's going to be easy. Okay, so the first thing that I'm going to do is square this square bracket. So I'm going to have -2 multiplied by 3, x minus 2, multiplied by 3x minus 2. Okay, I'm going to do that. -1. Just took the squared out, right? And then did it. So I'm doing this squaring. Now, I notice that in this chain of multiplication here, I have -2 times 3 times x minus 2 times 3 times x minus 2. My goal is to put this in vertex form. Rather than expanding that out fully and simplifying, I'm just going to notice that I can rewrite these elements in that chain of multiplication in a new order to very quickly put it into vertex form. So I'm going to notice that I can write this as -2 times 3 times 3 times x minus 2 times x minus 2 minus 1. I didn't do any operations there. I just reorganized the order of things. Okay? And now let's do that multiplication. -2 times 3 times 3, that's -18. X minus 2 times x minus 2 is x minus 2 squared. And -1 is -1. Hey, that's a function in vertex form. And it has a vertex. I can read the vertex because vertex form is usually a multiplied by x minus h squared plus k. Here, h is +2 and k is -1. So my vertex is at the point 2, -1. And yes, it has a very large a value. It's stretched by factor -18. So that's our new equation. That makes sense to me. Yeah. So that's how I would find the new equation there. I avoid as much work as possible and do it in the simplest way possible. Okay, now one thing that you can add to your notes here is if you wanted to create a transformation point, something like if I had a table of values that were all pairs of x, y values in the function f of x, how would I transform that into a point on g of x if I were going to be going point by point? And this is the way we would do it. We would take our x values we would divide them by k, and then after we did that, we would add 2 to them. Because let's take a look at the story of our x values here and what's happening to our x values. The first thing that we did was we compressed the function horizontally by factor 1/3. So we divided all our x values by 3. And then we translated it to the right 3 units. So we basically added 2 to all of our x's. So that's what the transformation of the x values looks like. And let's take a look at the transformation of the y values. We reflected it in the x-axis and stretched vertically by factor 2. So we're going to multiply our y values by -2. That's this number here. And then we were going to subtract 1 from them. So that's what a transformation point would look like to convert your table of values point by point if you wanted to work that way. Now we've seen this example from 3 different perspectives: working equation, working visually, and working. That's how you would work table of values. But we're going to look at some other examples where we go through a few points and apply these formulas. Okay. People need this algebra, or shall we carry on? Carry on? Okay, let's go. All right, so now let's describe the transformations that happened here to the function f of x, sure, equals 1 over x. This one here? Or do you want the transformation point? There, that's everything. There, look at that. Put it all on the overhead. Okay, everyone good? Okay, let's go. So, here we go. G of x is a transformed reciprocal function. I can see that it's the reciprocal function because we have an x and it's in the denominator. And it's also a linear one. I've seen, like you will see when you're doing your rational expression, sometimes an x squared will be on the bottom or some trinomial or something like that. But here we just have an x on the bottom.
What does the reciprocal mean? The reciprocal function mean again?
The reciprocal function means whatever input you give me, put it on the bottom of the fraction. So if you say my input is 10,000, then I would say, well, your output is 1 over 10,000.
Oh, it's the one that goes like this.
Yeah, and it has a negative component too. That's like reflected through the line y equals x. Okay, so it has 2 components. Its domain and range are x's of the reals and x is not equal to 0, and y's of the reals and y is not equal to 0. It has asymptotes that are the x-axis and the y-axis. Never touches those lines. This function, on the other hand, will touch those lines because it's been shifted to the left and right and up and down. So that's why this one will have x-intercepts and y-intercepts. So let's take a look at what transformations we would have to do to get this function. All right. Well, let's first look for any multiplications. I see that my base function is 1 over x, and this one is 3 over x. This is an A transformation. This was multiplying the whole function. So that basically stretches it up by factor 3. And that would be the first transformation that we'd have to do here. So here our transformations will be first stretch the function vertically by factor 3. So all of our y values are going up by 3. And next, we have some translations. And you want to put your right shoe on first or your left shoe on first? You want to do D or C? D? Okay, so second, translate the function. So we have a D transformation. The D transformation is right here, operating directly on those inputs. So I'm adding to my input here. What's that going to do to this function? Goes to the left by 1. Good. Yes, great. So translate the function. Can I get back in there? Yes, I can. Left by 1 unit. That's a result of D being equal to -1. Okay, because D is a weird sign flipper. All right, this one was because A equals 3 there. Good. And then last one, third, translate the function upwards by 2 units. That's the result of C being equal to 2. Okay. So that's how g of x is a transformation of f of x. How about we, Ali?
I don't know how you like find if it's an A transformation or B transformation.
So when I'm looking at which one of these transformations are which, I can consult like my parent function worksheet where we wrote out the different transformation forms of the different things. But I think that's a little cumbersome. You'll be flipping through a lot of pages and doing a lot of stuff like that to find the information. What you want to look for is, excuse me, I've had this frog in my throat. D transformations here are adding or subtracting to the x value. So if it was, say, a square root function like f of x equals x squared, sorry, the square root of x, and then you saw g of x, which is a transformation of the square root of x, and it were something like this, x minus 5 plus 10, like this. So here we want to notice that the minus 5 is inside the square root. It's connected to the x value. It happens before we do that square rooting, because whatever's underneath the square root sign, it effectively has a bracket around it to say do this part first and then take the square root of the result of x minus 5. So there we would notice that we can't have x values that are 4 or less or smaller than minus 5. Like x values would start at 5 and then increase because we can't take the square roots of negative numbers. So you can imagine that shifting the domain. When we've changed the domain in that way, that's a D transformation. It's moved our input values. This one over here is a C transformation. It's not connected directly to this x. It's outside of that square root sign, and it's just going to lift everything up by 10. So that's C. And then the tricky one to note here is what is this 3 doing here? That one is trickier to see. I agree. If I know that my base function is f of x is 1 over x, and then I imagine, well, how did that 1 become a 3? It didn't become a 3 by adding 2 to it. It became a 3 by multiplication. So that one would be, and I can't change that by just adding outside here. Like I can't say 1 over x plus some number c would equal 3 over x. I can't do that for some value c. There's no way to do that. Unless c happens to be 2 over x. But c is not a function, c is a constant. So it can't be 2 over x. So c? C here is 2. Yeah. So this doesn't work. There's no C that will do that. So the thing that happened to take 1 over x and make that 3 was we had to multiply this by 3. And that would equal 3 over x. So this here is multiplying the whole function. When you see something multiplying the whole function is in there happily in brackets, and the multiplication is happening outside. That's an A multiplication. That's an A. Multiplies the output, multiplies your Y values. If you had in here something like bracket, bracket, 6, this multiplication is happening directly to the X value. That's a K transformation. We don't have one of those here. That's why we only had 3 transformations for this example. Ty? Like, how do you mean? Yeah? Like right, like there. Yeah, like that's a 6. It maybe looks like a B. Let's change that value to something that's unambiguously a number. Suppose that we had a K value of 5. It would show up right there. Okay. And that would multiply your X and this D, but you would think of it just as squeezing the function by factor 5 towards the Y-axis. Yeah? Yeah. Do your A and K transformations first, and then your C and D transformations. because multiplication first before adding and subtracting. And then what else to say about this? I thought we could visualize this one in Desmos. Let's take a look. So we'll go kick open a Desmos here. And we're going to start with f of x is equal to 1 over x. And then let's prepare g of x, which is equal to 3 over x plus 1. Move outside that plus 2. And so now we'll see, actually, let's just take a look at it when it's 3 over x. There we see the effect of a stretch by factor 3. So the first thing that happened was we took this point here and stretched it 3 times. So that was the point -2, -1/2. Now it's the point -2, -3/2. This point here, 1, 1, is now the point 1, 3. That's a stretch by factor 3 vertically. And then we add 1 to the x value. Oh, Patrick, you had a question?
How would the k value affect that?
Oh, if we added a k value, let's say we go 3 over 5, then k is going to stretch things towards the y-axis by factor 1/5. So everything gets closer to the y-axis when I do that. See how tight that gets? Never, still won't touch the y-axis or the x-axis, even if I went to 500. Notice how tight that got to the y-axis, but it's never touching. It's still just like so close, but not there. You know, like during COVID, where you would see the footage of the nurse coming home to her family, and they had like a big plastic screen, and they would hug through the plastic screen. It's like that, so close and yet so far. Okay, so we didn't have a k transformation. Let's do x minus 1, and notice that it was x plus 1. It was x plus 1. Notice that it just shifted everything to the right 1 unit, to the left 1 unit. So as I was saying, we were going to get a y-intercept. There it is. There's our new y-intercept. Because now the line that it can't touch is x is equal to -1. Notice that x is equal to -1 would create a 0 here on the denominator, and we can't have that. So that's a limitation on the domain of this function. It effectively shifted it from x is 0 to x is -1, is now disallowed from the domain. And then the last thing that we did to this function was we lifted it up by 2. And as I said, we were going to get a y-intercept and an x-intercept. There's our x-intercept. There's our y-intercept. And now this function y can never be equal to 2. So even those asymptotes and the limitations on the domain and range can be moved around by these transformations.
Does the negative k value push it away?
Yes. So no, negative k will reflect in the y-axis. The things that will push it away from the y-axis are k values between 1 and 0, or between 1 and -1. Between 1 and -1. So let's put 1 in there. If I put in bracket here, and I'm going to bracket this bottom too, and then I put in a k value of 1 over 5, notice how far things have been pushed away from the y-axis. Actually, they're being pushed away from the line x is equal to -1, because I also shifted where the function is after we did that k transformation. Does that answer your question? Great. Okay, good questions, everyone. So, can you write g of x as a transformation of f of x? Yes, I can. And this is what it would look like. We would say, well, f of x equals 1 over x, all right? And g of x equals, well, I'm going to take f of x, and I'm going to multiply all of my inputs by 3. All my outputs by 3. And then I'm going to substitute in x plus 1 everywhere I see x, and I'm going to add 2 to it. So that's another way of writing g of x. That is equivalent to this. So you probably want to write that down while I take a sip of coffee and recharge from all of these excellent questions. Oh, because we have a d transformation of plus 1. So instead of substituting in an x, we would substitute an x plus 1 into f of x. and that would create this part of g of x.
So what does that f do? Like the 3f, what does the f do?
It says, I have defined f of x here. I am going to compose a new function g of x by doing things to f of x.
But isn't that looks more like vertex function, which would be.
But it's not. If f of x was x squared, then yes, this would translate directly to a vertex form for quadratic. But it's not. F of x is 1 over x. So let's. I can feel Oscar's confusion is not like localized to him alone. There's a lot of people that are looking at that being like, what are you doing? So let's actually follow it through, and I'll show you what this f of x is doing here. Okay, so let's go. And it's just doing your substitutions through function notation. So I'm going to follow this through, and we're going to see how this works. Purple. All right, so g of x is equal to, well, I'm going to do, I see f at x plus 1, so I'm going to substitute in f of x, but let's prepare f at x plus 1. This is f at x plus 1. This is 1 over x plus 1. That's what we would do, right? I just substitute in x plus 1 in place of x wherever I see it. So let's do that. But we're going to multiply it by 3. We're going to have 1 over x plus 1. That's f at x plus 1. And then I'm going to add 2 to it. Okay, last line, multiply this in, 3 over x plus 1 plus 2. Notice that that's the same thing we had underneath my face. There. See the connections that function notation can create here and allow you to manipulate functions into different functions, write them down in different ways. Or starting to do this, eh? Yeah. If I get you to here by the weekend, that's good. You can do a little bit of delta math practice. Next week, maybe it's like that, and then we've got a few practice days. These are weird ideas, but they're super intuitive once the rules get baked in. Malcolm?
So the 3f back at x plus 1 plus 2, is it just rearrange of the 3 over x plus 1 plus 2?
Yeah, it was like writing g of x as a transformation of f of x. So I know that the parent function for g of x is f of x, and I can just do things to that function to create g of x. Did that answer your question? Really? Sure. Okay. Yeah. So Oscar was saying, what's this f doing? Like, I'm used to seeing letters inside my math, and that means multiply by that number or something like that. But f is not a number. F is a function. Here it is here. It's 1 over x. And then this bracket here is telling me substitute x plus 1 in for x wherever you see it inside that function. And then multiply that function by 3. And then add 2 to it when you're done. So we do all those things. Then we get the new function g of x.
Sorry, but where did the g of x equals x minus 5 squared?
Oh, this? Oh, that was another example that I was talking about and saying, how do I recognize what these things are? That was a different function. I should have called it f of q of x and r of x or something like that. Bye-bye square root functions. Okay. Carry on, new example. Yay! Yay! So when you're graphing these transformations, you're going to want to be able to identify the parent function and then build it. You can build a table of values for the parent function as well and figure out what the different a, k, c, and d transformations you are doing, and then apply the transformations to x, y to obtain the map points. This is these are one way you can do your flowchart. You can do your flowchart many different ways. If you like following a recipe, this is a good recipe. But here, let me give you the ultimate recipe in my mind for working point by point. Know that x, y in the parent function, call it f of x, and g of x is the transform function. X, y will map to x over k plus D and AY plus C. And that will be how you map your XY points to your transformed XY points. Note that D is a sign flipper. As you pull D out of your equation, you flip its sign. That's why I have X over K plus D instead of minus D. I really struggle over the least confusing way to do that. I just remind you every time that I flip D's sign as soon as I look at it, when I pull it out. I think that actually matches my thinking, how I think about it too. So D is a weird sign flipper, and K is a weird flip to division instead of multiplication. Again, the opposite of addition is subtraction, and D shows you that opposition. And then the opposition of multiplication and division is those are opposites, and K shows you that opposition. Let's keep going. Cool. Let's go. So if we have a weird function that looks like something like the Big Dipper, but one of the stars went out, and we want to transform that based on all of these transformations here, well, let's see how we would do that. Here we don't have an equation for this thing. We could define an equation with like piecewise functions, saying it's a line that goes from a -3, 4 down to 1, -1, and then that's that part of the domain, and then after that it's this line, and then after that it's that line. But ain't nobody got time for that, to create 3 different equations and then transform each one separately. It would still work though. I'm not going to do that though. I'm just going to work point by point. So we have a nice table of values there for our parent function, which highlights these different points. And we're just going to transform them all based on all of these wacky transformations. So let's verbalize these first. I first notice that, and I'll do my multiplicative ones in orange, that I have a transformation here where I'm multiplying the output of the function. This is an A transformation, and it's 1/2. So that's going to affect my Y values. So I'm going to be multiplying my Y values by 1/2, so 1/2Y. For those of you who are following along and are good with fractions, note that that's the same thing as dividing by 2. Dividing by 2 is the same thing as multiplying by 1/2. And then I have this negative here. That's a K transformation. So I'm going to take my X values, and I'm also going to divide them by -1. Cool. Then I get to look at my translations. Here is a translation that will be shifting the entire function down by 2, subtracting 2 from all the outputs. This one is a Y transformation. So we're going to have -1/2 Y minus 2. And then this here, this is a D transformation. We are adding or subtracting directly to the X value. I see that it's +1, so I know to flip that sign as I pull it out. D is -1, and so I have X divided by -1 minus 1. Let's transform these point by point and then compare to what we would expect just looking at this visually. Okay? Verbalizing it, I am going to squish it by factor 1/2, reflect it in the y-axis, and then shift it to the left 1 and down 2. I had to pause there to get my left and right because I had flipped my hands, and I was like, wait, left is that way. No, it's not. Left is still that way. Very funny. Okay, so here, -3. Let's go. -3 divided by -1, 3. -1, 2. 4. 4 divided by 2, 2. -2, 0. See how I do that in my head and I skip a lot of steps and expect you to follow along with that arithmetic? There's people knocking at our door? The people have been knocking at our door for some time, haven't they? I'm not used to having the door closed. Hi, how are you all doing? Yeah, you need it? Need it for physics?
Yeah.
This one?
Yeah.
Yeah, there you go.
Thank you.
You're welcome. They're so patient. How long were they out there? 5 minutes? Anyway, they knock very softly. Okay, let's go. 1. 1 divided by -1. -1. Subtract another 1. -2. -1 divided by 1/2. Negative 1/2. Minus 2, negative 2 and 2 halves, or negative 5 halves? Need to see the algebra for that one? 1 over 2 times negative 1. I get the negative 1 here. I get the negative 1 over 2 here. Minus 2 equals negative 1 over 2 minus 4 over 2. That's 2 written a new way. That's minus 5 over 2. There you go. Okay, let's do this one. 2. 2 over negative 1. Negative 2. Minus 1. Minus 3. 3. 3 halves minus 2. Negative 1/2. Okay, 4 and 3. So that's going to be boop, 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 boop. 4 divided by this negative 4 minus 1, negative 5. Okay, 3 is still going to map to negative 1/2. Okay, all right, transform it point by point. Let's look visually. If we get, squeeze it by factor half, flip it in the y-axis, move it this way, this way. Let's see. All right, so, or let's A, K, C, and D. All right, so let's plot our points. 2, 0. Here's the point 2, 0. Boop. Here's the point negative 2, negative 5 halves. So this is negative 2, negative 1, negative 2, negative 2.5. That's negative 5 halves. All right, negative 3, negative 1/2 up here. And negative 5, negative 1/2 right there. So this is our new function. All right. Look at that. It's been squished vertically. It's been reflected, and then it's shifted over and down. Cool. Hi, Hannah. Okay. They haven't called here yet. But you better go, right? Yeah. I mean, what we're doing is really important, but you got something else going on. Let's go. Go for it. Go for it, Hannah. Yeah. Keep going. Keep going. Questions about this stuff? No. Working point by point. The real trick is finding these, right? Finding these. So if I use this idea here that xy maps to x over k plus d, ay plus c, then we would have a point that would basically look like what I have written down there, where xy will go to x over negative 1. I get the negative 1 there. Minus 1, comma, 1/2 y minus 2. Okay, that's your transformation point, what it would look like. All right, let's keep going. All right, here is the transform function of an absolute value function. Cool. So we remember that absolute value is just going to strip the signs out of there. Let's try it graphically first, and then try it transformations-wise. So we want to take a crack at describing the transformations that happen to create f of x. And notice this is annoying to me because we have f of x equals this, and then f of x is equal to that. That's a parent function. They should call this g of x. I should fix the PowerPoints if it bothers me. Okay, that should change that to g of x in your notes, not f of x. Malcolm, what happens to it?
Should the a value be negative 2?
Yep. And what's that negative 2 going to do as an a value?
It's gonna like flip it
Flip it this way or flip it this way?
this way.
Good. And then what does the 2 part of the negative 2 do?
How much it moves down?
Well, it's how much it stretches everything down.
Yeah.
Yeah.
That's fine.
Yeah, so that one's a stretch. When you say move it down, I think, or you mean translate? Because it's not translate, but it's definitely stretch.
Yeah.
Okay, great. And then we do have some translations here. What are the translations? Oh, also, no K transformation. Hooray! Did you just fist pump because there's no K? Yeah, good. Don't worry, we don't tend to use K transformations when they're equivalent in some way to A transformations. Like here, taking the absolute value and squeezing it towards the y-axis is the same thing as stretching everything up in some ways. Okay? So we'll generally write them as A transformations. But when we start looking at sinusoidal functions, K transformations are definitely different, and they make much more sense when you see the K transformations there. Malcolm?
I don't know if I'm right, but with DB1 and CB3,
Yeah. So we would expect the pointy part of this to be at the point 1, 3. So everything moved over 1 and up 3. And then, as Malcolm points out, it's going to be stretched down. It's going to look like this. Here's the new function. So I'm predicting that this is our new function. And let's just check algebraically. Here I am graphing very carefully, going the slope of -2 on one side and slope of 2 on the other side.
Wait, how do you know that's the vertex?
Oh, because Malcolm pointed out to me that this is a d of a positive 1. That's going to move it to the right by 1 and then up by 3. So I just knew that this point 0, 0 wouldn't be affected by this stretch here. So I moved that point 0, 0 over and up. And then I remembered that Malcolm told me that the whole shape had been reflected in the x-axis and then stretched by 2. So I worked visually first. Now let's work point by point to see what happens. Okay, -2, 2. So what happens to for our transformation functions? Well, our x values are just going to be x plus 1 because d is equal to 1 there. Okay, and then let's get rid of these. Okay, and then y values, well, we're going to multiply our y values by -2 because of a is -2. And then we're going to add 3 to them because c is 3. All right, let's try it. -2, 2. Well, if we do x plus 1, that's going to be -1. And then 2. 2 multiplied by -2 is -4. -4 plus 3 is 1. Oh, there it is. There's that point right there. -1, 1. We got that one. All right, -1, 1. All right, so -1 plus 1, 0. 1. -2 times 1. All right, -2. -2 plus 3, 1. Oh, look, there it is right there. Where? -1? Oh, this one?
Is that -1, -1, or is it -1?
Oh, it should be -1, -1, right? So 2, yeah, you're absolutely right. Yeah, -1, -1. Thank you, Miles. And here we go, 1, 1. We got that one correct. Let's go 0, 0. 0 plus 1, 1. 0 times -2, 0. Plus 3, 3. Okay, we got that one. That was the first one we did. And then 1, 1. 1 plus 1 is 2. And 1 times -2 is -2. Plus 3 is 1. So the point 2, 1. Oh, there it is right there. See how we're getting all those points? Cool. And 2, 2. 2 plus 1, 3. 2 times -2 is -4. -4 plus 3 is indeed -1. Thank you, Miles. There we go. It's down there. So we hit all the points that we got working visually, also working point by point, because the two methods are basically two different ways of thinking about the same thing. Allie.
Are there certain limits that always go into x and certain limits that always go into y?
D and K always affect your x values. A and C always affect your y values. D and K, yeah. You can think like Donkey Kong and Alice Cooper. Alice Cooper affects your outputs and Donkey Kong affects your inputs. Donkey Kong is always inputting barrels and like trying to squish you with them. Alice Cooper is trying to, I don't know, elevate your mood or something. I don't know what. Okay. You find your own metaphor with things that you think are cool. Okay. I'll use things that I think are cool.
And A and C.
I feel so old. All right. Let's keep going. All right, so we've got our parent function. We got a graph of it. And we've got a transformation here with all of the values. Youch. K values, A values, C values, D values. How will we manage this? You want to work visually? You want to work point by point? Let's go point by point first. So identify your A, K, C, and D. What is my A? 3. Good. What is my K? -1/2. Cool. What is my C? 1. What is my D? Yeah, let's do +2. Let's think about D as +2. We're going to flip the sign of D as we bring it out. Okay? Great. So now let's build our transformed function point. And remember, this is going to be x divided by k plus d. And this one is going to be ay plus c. All right, so So let's build those in here. X divided by k. Well, I don't want to write x divided by negative 1/2. So what should I write instead? Multiply by negative 2, yeah. Yeah, dividing by negative 1/2 is the same thing as multiplying by negative 2. So I am going to write negative 2x plus d is plus 2. And then a is 3, so we'd have 3y plus 1. Okay. Now people want to see y dividing by negative 1/2. Okay, so if I have my x values and I divide them by negative 1/2, this is the same thing as flip the bottom and multiply. So we flip the bottom and multiply, it's equal to negative 2x. Okay, the same thing. Same thing. Allie?
Wait, can you scroll up?
Yeah, there we go.
I don't understand the k, I mean s over k plus d like, do you always have one?
That's always the way k and d and a and c affect your x values and y values of any function.
Okay, so that's always the formula?
That's always the like point by point formula, yeah. That's something that if you like got a tattoo for this unit, that might be the tattoo. Put it on somewhere that's handy for the test. You just like take your wrist down and there it is right there. Maybe get one of the stick-on ones because you only need it for the test, and then after you've done the test, it's in your long-term memory. Put the tattoo in your long-term memory, not on your skin. I have no tattoos. I don't recommend them. Was that?
Do you sell them? Like, is this like a promotion?
I should make little math tattoos like the quadratic formula, and you can tattoo the quadratic formula on yourself. So it's like that would be yeah, like little cheat sheets. The
for cheating on your
yeah. Yeah, because how can they like tell you to take that off or something? It's like I got the tattoo. It's important to me to have this information. Okay, all right. If this really takes off, I'll take 5% of the proceeds and distribute it amongst all of you. Okay, so maybe we all just got rich, me especially. Yeah. Okay. All right, you heard it here first, folks. Let's see, 0, 0. Well, I know that these multiplications don't affect 0, 0, but only the additions. So this is just 2, 1. People follow my logic there? Yeah, very fast, right? 2, 1. So the starting point of this function moved over here. Notice that we can only use x values that are 2 or bigger because anything smaller than 2 would create a negative number inside the square root. And we don't take the square root of negative numbers yet. So, yeah. All right. It's not that hard. It's just you just add an I afterwards, and then they do all weird complex things in the complex plane. It's super fun. I like doing them for mental math practice. He says trying to, a math teacher math flexing on his math students is about the lamest thing I can be in this moment. So let's keep going. 1, 1. So we take 1 and multiply it by negative 2, and then add 2 to it. Oh, I know what 1 times negative 2 plus 2 is. It's 0. And then 1. 1 times 3 plus 1 is 4. Okay, 4, 2. That is going to be negative 8 plus 2 is negative 6. And then 2, this is going to be 6 plus 1 is 7. Okay. 9, 3. Well, we're already off our graph here. That's going to be a negative 18 plus 2 is negative 16. Am I right? I think I'm right. I'm right. Okay. And then 3, this is 9 is 10. Okay, and then 16, 14. Oh, come on. We're way off the graph here. This is minus 30. And 4, that's going to be 13. But we're going to write it down because 13 is one of my favorite numbers. Can't resist. Chance to write it down. Okay. Let's also just prepare ourselves for what we're going to see visually when we graph this. We should see that everything has been stretched vertically by factor 3, stretched horizontally, and reflected in the y-axis by factor 2. Things are going to be further from the y-axis because k is between 0 and 1. Okay? Well, it's between 0 and negative 1. And then also things have been shifted to the right and up. So let's see what we get. So 2, 1, 0, 4. So we got 0, 4. Boom. Okay, up there. We got negative 6, positive 7 up there. And negative 16, it's about here. And positive 10, so it's about there. Okay, we can graph off the graph. You can just kind of predict it. And then it looks like this. Whee. There you go. So we see that reflection in the y-axis. We see that everything is shifted over and up, and it's all grown this way and then grown that way. Cool. Sorry? Yay. All right. So feast yourself on some of this with the next 10 minutes of your lives. I'm glad we got to go through lots of examples together, folks. I'm glad. And any questions, hit me up by email or bring me over to your tables now. And thank you for your participation in the lesson.